Welcome again for the next tutorial about Matlab in combination with the project for transportation systems. Last time we created some methods or scripts to read data from an Excel file where we had the raw data. And before we come to the next tasks here to use the real sensor names and also to calculate an aggregation or a mean for a special time period, I want to come back to one question which came up during the last live tutorial, because some of the newer versions with Matlab had problems with readtable because you saw a different setup in the table. The names of the columns were different, and therefore I searched for a solution, and I hope that the coming next 2 minutes will give you a solution. So please try it with the version 2020 and then let me know if it works. So let's directly jump to the readtable version. Before I come to that, I did the following. I created 3 different files, one with the reading of text files with the raw data, another with xlsread, and another with readtable, so that I have now 3 different scripts, and it depends on which script I call, then I do the different reading method. Okay, so let's jump to the problem with readtable. So this is the script which we used for reading the data using readtable. And the problem was that the different versions of Matlab read the table with different names of the columns. And therefore I searched for a solution which reads the whole table as it is, so that there are no changes. And therefore we just changed the following. We changed the readtable and we add some attribute pairs which are called read variable names and read row names, and you can set it true or false. In the standard reading method it's true, and if you name it false, then it is not used and the whole table is read. So no values are used to define the names of the columns. If we do this, then we have also to change the following statement of the remove missing data, because the elements between the sensor names are now filled with empty character strings, and therefore it would delete the whole table. So what we can do is we just add missing number, or a mean missing number of elements which we require for the deleting. So minimum number of missing elements is again a pair of attributes. This is often used in Matlab so that you can have a different order. So you can, for example, use this in a different order, so that you can make this, for example, so that you have a different order in these sets of attributes. And if you do this, so read rows names and read variable names false, and if you delete only columns, so the second dimension, which is the columns dimension, and only if there are 2 missing elements, so 2 missing values, then you will get what you need. What you also have to change is, of course, the selector, because now you have in the first line really the names of the sensors, in the second line really the names of the columns in this raw data Excel. So to go back to what we have in the Excel is this. So if I open this Excel, you see the first line are the sensor names, the second line is with the column names, and now you have really this table available in your Matlab program, and therefore you have to change this, because we have now to start at the 3rd line, and therefore we changed this to the 3rd line. And with this changes, now everything should work. So let's try it. Oh, I deleted clear, so let's do this. and now it should work. And it reads now the data. Readtable is not so fast, therefore it costs a little bit of time. But finally, you will get the data as they were in the Excel file. So if I go to the raw data table, you now see really the complete table as it is. And if you watch the old video, you see that MQ69 is the name of the column in this table, and therefore now you have really the table, and you can just call the different columns with the var1, var2, var3, and so on. So with a created version of naming. With this, you should have now the same situation as I have it in my version, and therefore we can continue with the next steps. So the next steps are shown here. So they extend the existing programs or scripts with additional possibilities. And the next steps should be that we really use data which we have available. So for example, the sensor names and the real timing. Why is it the problem? So for example, if we have missing data, so if a sensor breaks during the saving of data, then we would have a gap. And if the sensor starts again, then it's not just the end of the file, there will be a gap in the middle of the data, and therefore we have to use it that we get really the timing elements which we need. And therefore we now use the real sensor names and we use real times. And what we also want to do, we want to create a plot that we have all, let's say, limits of the plots in the same range. Because if you want to compare the different graphs, it's easier if you have always x and y in the same range. And this is quite important for comparison of different data sets, of different raw data sets. And finally, we will do an aggregation calculation. But let's first start. So as I said, I have now 3 different files, one with with load, one with xlsread, and one with readtable. And we have to create all of these 3 different files with the same functionality. Let's start with the first one, readtable. So let's extend readtable with a version, that allows us to use the real sensor names. So let's go to Matlab. So this is the version which we changed before, and now we want to use the real sensor names and the real timing. So let's start directly with the timing. What we have to replace is this. We do not create an artificial vector. We now really want to use the values which we read from the raw data. So we create the time vector, and we watch our raw data where the time vector is located. So in our case, it's on the first column, or in the first column. And we start here at the 3rd line. So we can now select all values from there which contain time information. So we do this with a selector. So the same thing what we did here. We use the 3rd line to the end, and we take the first column. And then we create a vector which contains real values, so real number values. So here we have a cell vector which contains character strings, and here we have really the values which can be used for the calculation. And then we do exactly the same what we did here. So we run through all of the values of the cell matrix, and we convert it with string to num to real numbers. So in our case, we just have a vector, so we just need one for loop. So we run through all of the lines here with a row counter from 1 to size of time cell vector, first dimension, and then we do exactly the same what we did here. we take the value, the character value from the time cell vector and convert it with string to num to a real number. And then we want to transpose it so that the x-axis is a line vector, and therefore we do time equal time transpose. And what we have now to do is, in our case, we have the representation of a minute, which is Excel specific. So this is exactly the fraction of a minute of 1 day. And we know now that this is 0 minutes and this is 1 minute. So if we want to have integer numbers, then we have to divide all values by this 1 minute value. And this can be done quite easily if we do the following. So if we take the time vector and we take the second value in this time vector and divide all elements in this time vector element by element with this scalar. And then we have one problem that we get rounding errors, because it might happen that there is a fractional part in one of the last places after the floating point, and therefore we have to round the output so that we always get complete full integer numbers, and then we assign this again to the time vector. So what we have now is a version which calculates or which creates the time vector from our real raw data. And this is quite important, that we don't have some problems with gaps in the raw data, and that we do not automatically create our time vector. So if I open this time vector here, then you will see that we have a continuous time setting from 0 to 1414. So this is the first step. The second step is that we want now to get our sensor names, and our sensor names can be fetched also from the real data. So our sensor names are located, if you watch our raw table, then are our sensor names in the first line. So what we just take is, we take the first line, again the same stuff what we already know. So therefore I told you in the theoretical lessons that it's quite important to deal with these index selection mechanisms with the colon operators and so on, because it will happen all the time during Matlab programming. So what we do, we take the raw data table, we use the first line and take the whole line and bring it into a new matrix, which is called a cell matrix, because we will have text versions and we will have all of the parts here which we need for our sensor names. So, and finally we have now collected all of the sensor names, but there is a problem that they're empty values. So we have in between the sensor of the sensor names, we have no elements, and therefore, or we have empty strings, and therefore we have to use the same thing what we did in the beginning here. We have to delete missing data. In our case, we can delete all missing data, and again in the second dimension, because we want to delete the columns which have missing data. With this, we get now a vector, a cell vector or a cell array which contains all sensor names. And finally, we now want to flip the sensor names, because if you remember, we have the speed data in a version where the sensor with the closest distance to Munich is located in the first position, and therefore we have to do the same here for the sensor names, so that the first sensor is, or the first sensor name is also the sensor name for the sensor closest to Munich. So if we run this, we will have now all values which we need for the plotting. Let's have a look. As I said, readtable costs a little bit of time. But if it finishes, then you have sensor names here. And if I open this, you see all of the sensor names which you directly read from the raw data. So we can now change our plotting mechanism so that we use this real data. So this is our plotting mechanism, and this plotting can now be changed. So we changed the readtable version. So this is our version which I used, the explanation step by step. So I call this version, and then it plots all of the data. So we already used a time vector here for the x-axis. This time vector is now the new time vector with the generated parts from the raw data. Therefore, we don't have to change these parts here. What we have to change is this title. So let's set a command that here are the title settings for our data. And what we do now is we replace this num to string, where we use the counter here for the version of our text title. We replace it with the real sensor name, and we want to set also directly a specific font size. So what we do is we now use the sensor names with this curly brace. So it's a cell matrix access into a vector of the sensor names, and we take the sensor names and we combine it. So this is a new vector which combines the two text parts, the sensor and the sensor name, to a new text vector, and we directly set the font size, in our case to 12. So if we do this, then we directly have the headlines with the real sensor names and with the real time version. What we also can do is we want to have the same limits for our plots, and therefore we can directly add what we need for the limits. So in our case, the limits for the x-axis are quite simple, because we know that the maximum x-axis part is the number of time slots. So it doesn't matter how many elements we have, we just take the number of time slots. Or we take the maximum of the time vector. So this is also possible, so that we take max of time in this case. And another part for the y-axis is that we take max of speed. So in this case, we do the following. And what we get is now a version where we have the maximum values defined for all of the parts. To speed the run a little bit up, we can calculate the max speed here, so that we don't have to do the calculation all the time during the run of the program of this for loop. And we also can define max time here, so that we have it also available and that we just have to call it and not to calculate it all the time. And therefore we use here max time and max speed. And with this, we have now an updated version of our plotting mechanism. And if I run it, you will see that it will plot our data. And the plotted data look now like this. So if I zoom in, you see now sensor with a real sensor name. All of the limits are comparable, so that you have a real nice plot now. So this is the solution for the first two tasks. We now have just one problem, that we have 3 different versions to read the data. And therefore we have to update these things as well, so that all of the scripts after the running produce the same result. So that we can use the plot script with all of our other scripts. And therefore we have to update all of these scripts as well. Let's do this. So this is our xlsread. which we created last week. And therefore, we can now update this version in the same style so that we have the sensor names and also the data for the time from the raw data. So first of all, let's run it so that we have the raw data as they are with this new version of the reading. So if we watch the raw data, then we have the sensor data available there. And we now have to collect again the sensor names here and also the columns or the rows from here. So let's start again with the time vector. So again, we replace this time vector, create time vector. And we do the following. So we select from num data, because here, this is the nice thing from xlsread, that it directly separates num data, text data, and raw data. So we can directly take the num data, select all lines of the first column, and then we directly have the time available. And we directly have the time available in number representation. So we don't have to convert it anymore. And therefore, we do exactly the same what you already know from the other script which we prepared before. So we transpose the data that we get the line vector, and then we divide by the second element, which is the representation or the fractional representation or the floating point representation of our 1 minute element. So if we divide all of them by 1 minute fractional part, then we will get complete integer values, and again with a round. So with this, we have done the whole stuff. Let's continue with the sensor names. So the sensor names can be taken from the text data. So therefore, we directly fetch the sensor names. And also here, it's quite simple, because we know that at each 8th position, we will have a new sensor name. So let's fetch these things. In the text version, it is already a cell matrix. So we take this and say, let's create all sensor names. And we automatically delete the empty elements, because in our selection mechanism, we directly take each 8th position. So after this step, we have all data available. The only problem here is, if you watch into the raw data, then you will see that at the end, there are additional elements. So if I run this program, and if I ask for the size of sensor names, then you will see that we will get more than 19 elements. So if I go into sensor names, you'll see it looks like you would expect it. But if I go to size of sensor names, then you will see that we have 22 elements. And this is because there are additional empty columns at the end, and therefore we have to delete these empty columns. So this is quite simple, because we already know the number of sensors. The number of sensors is created here. So therefore, we can check if the size of sensor names in the second dimension, so in the number of columns, is larger than the number of sensors. So if this does not fit, so if the sensor names has more columns than the number of sensors, then we delete the rest. And deleting the rest is again using this colon operator. So we start at number of sensors plus 1, so the next, and go to the end and delete everything what we find there. And with this extension, we now have the same situation what we prepared before, and we can now directly plot the data again. So we switch to the plotting mechanism. And we use here not readtable, but we use the version xlsread. So this is our script, which we changed, and we can now call this script. So let's run it and let's see if everything works. And what we now have is a second version of the reading. So the first one is readtable, the second one is xlsread, and we have everything updated to a version which is available and usable for the plotting mechanism. So this is a real nice stuff. And now we have to update our version for the normal reading of text files. And here we have a problem because with load we cannot get the data as we need it. So therefore we have to change into a new version of text reading, and this we will see later on in our course. Therefore I have to do a workaround here, which is not nice. So it's not what a programmer would do, because we will create artificial vectors for the sensor names so that we can use the raw data, or that we can use the reading of the raw data just for the numbers using the text read with load, and we create the rest manually in the script. And therefore we can use the different versions of reading for the plot, but for the text version it's not, let's say, the sophisticated style. Okay, so let's go to this. So this is what we have for the reading, and now we cannot create the time vector because there is no time read, so we cannot use this mechanism. We would have to use functions which are for the low-level reading, all of these file functions. So this means we would have to use the fopen, fgets, fclose, and so on, so that we really read the file, and then we parse the file and separate the single pieces manually in the script, and this we will see later in the course. For now, we have to keep this version of the time vector, and we have to create a matrix or a cell matrix which has the sensor names. So what we do is we create a matrix, and we call it sensor names, and then we open a curly brace. So the normal thing what you know from matrices, just without the square brackets. And we now add sensor name by sensor name. So the first one is MQ50, the next one is MQ52, and so on, so that we create a matrix which all with all sensor names. So, and in this case we now just have a mechanism which works just for the raw data of one special style. So if the raw data would change, that we have more sensors available, things like that, then it would break, while the rest, so xlsread or table read, would still work. And this is what is not so nice in our mechanism here, but it will work. So therefore, if we again open the plotting, then we can now use also the next version, ts read step by step. So this is our reading of the text or simple text versions. So if you run it, it will work. So what is not so nice now is that we have now 3 different versions, and we have to manually select during the call that we want to use one of these. And therefore I want to replace this part here by a mechanism which we saw in the theory. So by a selection mechanism where we ask the user which reading method should be used. And therefore we do a switch case statement where we ask for a special input. What we do is we prepare a menu where the user can select 1, 2, or 3, and it depends on what is selected. The individual reading method is called. So what we do now is we create a menu, which is nothing more than an output of different text. So please enter a reading method. 1 is load, 2 is readtable, 3 is xlsread. And then we ask the user for a special selection. And after reading this, we now have a selected method, which we can now separate with the if-else condition, or as we just compare always with the equal comparison, we can use the switch case method. In our case, we compare reading method, so the input from here, and we compare it with 1, 2, or 3. So in case of 1, we do the following. We call the load method. So we call this one. And in case of 2, we call the read table version. And in case of 3, we call the xlsread version. So that we can select now the different mechanisms. The problem is now if the user enters something different to these 3 numbers. So you have always to expect that a user will enter a value which is not what you would expect. And therefore you have to adapt the thing so that you directly solve this error, so that the user has another chance to enter a new input. And therefore we change it, and this can be done easily if we set a while loop. So you directly see that I used other indenting here because I also directly knew that I have to use here a while loop. And the while loop runs endlessly as long as the user enters one of these versions. And that we can stop this while loop, we'll do a break here. So let's have a look into this. What happens here? So the loop starts, and we ask for the first version. If we enter something different, so if it does not fit, we will never end up here in one of these break statements. So we will go to the next, and this part will be printed again, and we ask for the next selection. So we'll ask endlessly for the next selection, so that we directly will continue as long as the user will enter one of our expected values. And therefore, we directly avoid this error situation. So let's do this. Let's run the program. And now we'll see here, so I close the outputs here, we directly see our selector mechanism here. So where we have a menu, and if I do an enter of, or if I enter 2 here, then I will select the read table version. You see it, this is our output from the script file, which reads the table with read table. And then we'll do the plotting, the reading and the plotting. So if I call it again, and if I select, for example, 3, then you will see the difference. Now it reads the table with xlsread. And we'll do the plotting. So therefore, we have now a menu where we can change the behavior without changing the program. And this is always what we want, that we do not have to rewrite the program. We just want to call the program. And with this, we finished our first 2 tasks. So add real sensor names and real timing, and find the minimum and maximum speed so that we can plot it. And we did it for all of our 3 different methods to read the data. So now we have to go to task 3, which is doing the aggregation calculation. Therefore, we open a new editor window and we save it in a new file, ts-aggregate or ts-aggregation underline step by step, because I explain it step by step here. So we change to a new empty window, and then we do the programming. So what does it mean? I switch to my external camera, and we want to do now the following. So if you remember, we have the raw data in the following style. So we have an x-axis, we have a y-axis, this is the time, and this is the speed. And then we have the speed data. And what we want to do now is we want to create now intervals of 15 minutes. So that this is 15, 30, 45, and so on. And we want to calculate the mean value for this interval. So from, in this case, from 0 or from 1, index 1, or from 0, in my case, from the minutes, to 14. And then we want to calculate the next mean, and the next mean, and the next mean, and the next mean, and so on. So that we get at the end such a rectangular or step function, where each is the interval of 0 to 14, or in index from 1 to 14 index, the first 15 minutes. What we do to create this is that we select now each time such an interval, and then we calculate the mean. So if you hear the word mean, then you should directly check if there is a function which you know from Matlab, and of course it is. So there is a function called mean, where we enter the interval, and then you get one single scalar for this interval, and you do it for all of these steps: mean 2, mean 3, mean 4. So, and to simplify the plotting, if we create again a vector which is exactly the same size like the raw data, but where all the time 15 elements have the same value, which is the mean, so that we have mean 1, mean 1, mean 1, and so on. And then for the next interval, mean 2, mean 2, mean 2, and so on. Then we simplify this, and therefore we convert this, that the mean is spread again to the positions. And this we have to program now. So in the first step, we can simply do the following, that we just copy what we know from the plot. This means we first of all clear everything, and then we call our standard plotting, and we write a statement what we want to do now. So we calculate the aggregated data. The rest is very similar to what we know from the plotting. So we just copy now what we know from the plotting. But from here to here, in between, we have to do the mean calculation. And here we have to start with additional work. So a first step is that we don't work on the real speed matrix. Let's do a copy of the speed matrix. So let's copy the matrix which we have, and let's just work on this copied version, on the aggregation here. And what we now do is we now select, let's start with one sensor, with the first sensor. We now select the values which we need for our mean calculation. Selecting is exactly what we know, aggregation, and we select here the first sensor, and then we want 1 to 15. And this part is now fed into the mean function. So with this, we get one scalar of the first 15 elements, or one scalar which represents the mean of the first 15 elements of the first sensor. And Matlab is so nice to us, because if we assign this single scalar again to a whole range of elements, where we just copy what we already use for the mean calculation, then it directly splits all of these elements to these 15 elements again. Okay. And then we have to do it again for the next part. So in this case, for 16 to 30. And so on. So if you see this, then you should directly come to the idea, okay, we need a for loop. So let's stay in the situation that we want to calculate for the first sensor. So we now write a for loop where we do this indexing here automatically. So we have a for loop of mean interval counter starting from 1. So here we go to each 15th element. So 1 plus 15 is 16. So we have an iterator of 15, and we end up in the number of time slots, because this is the maximum number of elements which we have. And then we do what we defined here manually for these new intervals. So the first sensor again, and now we use the interval counter. So we start from mean interval and we go to mean interval, but here now plus 14. So that we have 1 plus 14 is 15, which are the first 15 elements. And then we just copy what we have here, so mean, and inside as a handover argument, we again do the same here. And that's it. So with this loop, and now we can delete this, if you compare this, it's exactly what we have here, just that we replace these values with dynamic values. The first one, which is the mean interval counter, and the other one which is derived from this mean interval counter. So we just replace these static values by dynamic values, and we calculate the means for one sensor. But we want to do it for all sensors, so we need another replacement of a static number. And this is this one here. So now we want to count through all of the sensors. So for detector or sensor count, you can name it as you want, 1 to number of sensors. And now we go through all of these sensors and we replace the static one by the dynamically counted sensor count. So we start with sensor 1, we do all of the mean calculations, we go to sensor 2, do all of the mean calculation, and so on, and always replace 15 elements with the same value. And that's it. So with this we calculate the mean. What we can do is we can replace or we can delete things which we do not need later on. So we can clear, for example, the detector count, because we don't want to waste space in our workspace. So therefore we clear things which will be in our workspace but not needed anymore. So let's delete these counters here, and then we clean up everything. So let's go to the plotting. So if you remember, we plot in a new figure, and if you remember that plot allows you to plot different different raw data sets. If you just repeat x and y definitions, then it's easy to do what we need. So we have a new x, which is the same time vector, and we have a new y, which is the aggregation. And the plot counter defines our sensor. So we take all of the data for an individual sensor. You could also rename this plot count by sensor count or whatever, or by detector count. It's exactly the same here. And then we run through all of this, and Matlab decides the color automatically. If you want to set the color as defined in the task, then the speed raw data should be blue, and the mean data should be red. So, and with this, you can now plot the data. So let's test it. By the way, I had a typo here. I meanwhile updated it. So aggregation, there was a missing A. So please also correct this. And let's run the program. So we can select now. Let's do the read table version. And it will plot now a first figure with the raw data in blue, and a second figure with the raw data in blue and the mean data in red. So here are the figures. This is the first figure, and this is the second figure. So, and if you watch this, now you see that you have these mean values available, and you can zoom in here so that you see this step function. It's not really a step function, what you see here, for example, because we do an interpolation. If you want a real step function, then it would be necessary that you make really x values which are the same for the point where you have this jump. But for the normal representation, what we have here, it should be enough to have this ramp between the steps, so that the plot does the interpolation automatically. Otherwise, you need a little bit more. You can play with this. Okay. So this is the solution for task 3, and therefore we can go to a version of the next tasks where you have to play a little bit with the data. Especially if I zoom out here again, you will see that there are data which represents strange numbers. For example, -1. And a car with a speed of -1 on a motorway is strange. So therefore, there must be something with this -1. And these are the next tasks which you should solve for the next week. So let's play with this. So the next tasks are that you should first of all understand what are the -1s. Then you will see that these are outliers. Must have to do something with the sensor situations. So maybe with error situations, think about that. And then we have to avoid these outliers, because if you check this, you will see that the situations where a lot of outliers are and where the speed difference is very high, you will have very different scenarios of the mean, even if you have the arithmetic mean. Okay, so therefore you should play with these outliers, and you should directly check also how you can avoid these outliers so that the raw data are reduced by these -1s. And then you see in the project description, so go back to the video about the project descriptions, you see there that there is a method which is a Q-weighted mean, which is much better for the use in these data sets. So write a function. Now we go into the function writing. You will learn a lot of more function writing if we redesign our code to a more sophisticated solution in the next lessons. But here you start with a function writing. So write a function which is named QMean, and it should be used like the normal mean, so that you call QMean instead of mean, and then use a Q-weighted mean calculation. And then, as we have now 3 different versions, the normal mean, the arithmetic mean, the normal mean with the outlier avoidance, and the Q-mean, you can now compare the data. So write a small program or script which calculates the means and which compares the different means. For one sensor, this is enough. You can do it for all sensors, but it's enough for one sensor. And zoom in so that you directly see, for example, here between 0 and 400 minutes or whatever. So these are the new tasks. I hope you will have fun. See each other. Stay safe. I have a new mask. Stay safe. And we see each other next week.